The first derivative test. Remember that the first derivative is used to find out whether a graph is increasing or decreasing. If the derivative is greater than 0, then the slope of the line is increasing. If the derivative is less than 0, then the graph is decreasing. And you use the first derivative to find the critical numbers. And when you get those critical numbers from factoring the derivative, you check those critical numbers into the original equation to determine the maximum and the minimum values. So the first derivative test states that if c is the critical number of a continuous function, then for 1, if the derivative changes from positive to negative, then we found a local or relative max at the point C. If the first derivative changes from a negative to a positive at C, at the critical number, then f has a local or relative minimum at C. So you're looking at where the derivative changes, and if the slope of it does change, then we're locating a local max or a local min. If the derivative does not change at the critical number, then f has no maximum or minimum point. So find the local maximum and minimum point of this cubic graph. So the first thing that we need to do is take the derivative of this equation. And the derivative of this equation becomes 3x squared minus 6x plus 3. We're going to next find the critical number. So in order to find the critical number, we factor out a GCF of 3 and find the critical number to be 1. So if we make a graph and locate the critical number, I picked the points 0 and 2 on the left and right of that critical number. So I'm going to test in the points 0 into the derivative, and I notice that it's 3. At 2, when I plug 2 into the derivative, the answer is 3 as well. So since it didn't change, the sign didn't change, it's both positive, then there's no local or relative max or min point. And you can see that the derivative of a cubic is x squared, which is a parabola. So if you were to punch in to your graphing calculator x cubed minus 3x squared plus 3x, you'd get a cubic graph going through the point x value of 1. In example 2, it says find the local max and min of f of x equals x cubed minus 3x plus 3. Oh, and you can see that it is a cubic graph. So this is the same equation from example 1. So there's no max and no min value. Here's our next example. So our next example is f of x equals 3x to the 5th minus 5x cubed. So the first thing we'll do again is find the first derivative, because the first derivative is the slope of the line, and then I will factor the derivative to find the critical numbers. So there's my first derivative of 15x to the 4th minus 15x squared. I'm going to factor out a GCF of 15x squared. And I will find that my critical numbers are 0, 1, and negative 1. So if I plug in these critical numbers back into the original graph, you see that f of 0 equals 0. If I plug in 1, my y value is -2. If I plug in -1 into the original graph, my y value is 2. So I have a local max at -1, 2, and a local min at 1, -2. So you could start sketching this graph just to get a visual of what it would look like. If I use the derivative and pick points on the left and right of my critical numbers, that's how I determine if the graph is increasing or decreasing. So I don't actually have to come up with a number. I just need to know, is it positive? If it's positive, it's increasing. If the value is negative, then it's decreasing. So you'll notice when I plugged in -2 into the derivative, I did calculate it to be 180. So since it's positive, then it's increasing at -2 up to my local maximum point. When I plug into the derivative -0.5, I get a negative value from the derivative. So the graph decreases to my critical value of 0. Then I plug in 0.5 into the derivative, and it's still a negative value. So the graph still continues to decrease. And at 2, it's positive because I plug the number 2 into the x value of the derivative. And it's a positive value, so I know that it increases. And I've obtained this sketch on the right by plugging in my values. So again, take the critical numbers, plug it into the original for the max and min points. When you're using other points into the derivative, you're finding out whether the curve increases or decreases, which is the slope of the line.